Right, 'cause it's Saturday night. Do. Oh, hello there. Oh, what's this? Oh, looks like the number or the symbols and stuff and things for the Boltzmann constant. Well, you all know what that means. We conjecture ahead.
Although this is going to be weird, and it's going to be about a different.
Title of the conference was something like "Ground Truth" or "Turtles All the Way Down," and so it seems as though there's one Roolead. I don't think it rules them all, and it might be just hyper Ruleo turtles all the way down.
Yes, it's on the back of an infinite number of hyper Ruleo turtles.
Various people are commenting on the outrage of hacking the universe on a MacBook Air.
Hey guys, memes here. So, what the heck is the Boltzmann constant? We go to our friend Wikipedia. Links are in the doobly-doo. The Boltzmann constant, Kb or K, is the proportionality factor that relates the average kinetic energy of particles in a gas with the thermodynamic temperature of the gas. It occurs in the definitions of the Kelvin and the gas constant, and in Planck's law of blackbody radiation and Boltzmann's entropy formula, and is used in calculating thermal noise and resistors. That sounds important. The Boltzmann constant has dimensions of energy divided by temperature, the same as entropy. It is named after Austrian scientist Ludwig Boltzmann. I want to throw a von in there. I apologize for my statism. But what do we got here? Yes, as we all know, and we discussed this before. Hey, Whitechapel. Thank you for joining, my friend. Saying hi to us now and temporally in the future. But in 2019, they redefined SI, basically to help make it more coherent, because the metric system, especially the scientific units that we use, we want them to be consistent over all the different constants and stuff, right? Because if a system is coherent and you use the appropriate units, at least according to something on Wikipedia, the rest of physics then becomes true. Basically, you need force times equals mass times acceleration, energy equals force times distance, and then power is energy divided by time. So that's pretty cool, especially if it's true. But all right, so we got the number here, 1.3 80649 times 10 to the negative 23 joules per Kelvin to the negative 1. Oh my God, what is that? Let's go to a friendlier thing. It was brought to us by NIST. So they have the little meet the constants thing. They have this cool little diagram and stuff. We go to the speed of light, Planck's constant. I think we did that the other day. Yep. Okay. All right, K, the Boltzmann constant. The Boltzmann constant relates to an object's energy to its temperature. In the revised SI, the Boltzmann constant K equals 1.380649 times 10 to the negative 23 joules per Kelvin. K will help to define the Kelvin. Groovy. And then they have a little bit more of a section here. They go into, someone's like, oh my God, look at that beard! It's quite majestic if I do say so myself. But basically, here's the Maxwell-Boltzmann distribution. As we can see over here, we got the number of particles. We got the speed of the particles. You see the most probable speed, the largest number of particles are traveling at this speed. Then you get the average speed. The average particle speed is slightly higher than the most probable speed because this distribution is not symmetrical. You see it kind of goes up there and goes down there. Cool. And they basically say the same thing here, because in 2017, the world measurement science community met their requirements for giving the Boltzmann constant an exact value and redefining the Kelvin. Acoustic thermometry, DCGT, and JNT measurements from various research groups, I have no idea what those acronyms mean, were used in the final determination of the Boltzmann constant for the redefinition of the SI that was approved in November 2018. Based on these data, the value of K sub B is in the revised SI is 1.380649 times 10 to the negative 23 joules per Kelvin. Okay. Now, and they go into how it was not based on a physical artifact as the kilogram was for mass, but its redefinition apparently is just as momentous, they're saying. I guess this is important. Okay. What we got here? So, again, just Boltzmann constant, because if you put this into Wolfram Alpha, it gives us some numbers there. We'll get back to that in just a second. Okay. What's this first thing here I was showing here? This is from at least probably the most upcoming, I'm sorry Thad, I believe it's mostly publicly out there, probably in the third volume of Thad's book 44, Derangements and the Shape of Persistence. This is basically as we see here. We have K sub B. It's the Boltzmann constant, the symbol. Ain't that pretty? Now, if we utilize the universal binomial factorization equation, what we get? Well, we try to figure out what things the stuff we're talking about are doing. Okay, so you have the primary action times the boundaries, and times the terminal action. Okay, so, oh, what's this? Memes, you're wrong. Why? These are just boundaries. You showed us this before. This is the Planck length squared times the Planck mass. That's divided by the Planck time, again, the small t. Don't confuse it like I have a bunch of times. Squared times the Planck temperature, the big T. Yes. Now, where's the primary action? Well, my friends, the very interesting thing is every once in a while, primary action can be 1. And people think 1 doesn't necessarily do anything. I'm just saying that it might be kind of important. Just my opinion as a dude on the internet, to return to our equation. As we can see here. Alright, so we got 1, that's our primary action, times our boundary condition. We'll get out to about 4 or 5 decimal places or so. What's the terminal action here? So, its prescription is 1 plus, what's this? 4 pi? That seems to be a sphere. So we got like a sphere doing a thing. What's the other thing it's doing in here? Okay. What's this? This is J1 plus J2. What are those things? I forgot to link the hyperbolic vortex equation in this one. But here's our hyperbolic vortex equation. We got that 1 over x plus x cubed divided by 2 pi. We set that equal I raised to the I. So the imaginary number raised to the imaginary number. And we raise that to negative pi divided by 2. So that's a little twist. And you got a big twist over here. Big twist, little twist. And then we subtract out the Planck mass gap. We'll still get into how we generate this at one point. But, okay, our J1 is this. We got our J2 is this. We see, we add those together, and then we multiply that by the terminal boundary, or the point of inversion in and of itself, where it's basically has the boundary action here. Because if you pay attention long enough, a lot of times right around 7 decimal places, so, and this happens to be, was it Planck mass times Planck length, divided by the Planck charge squared, which coincidentally comes out to be 10 raised to the negative 7. That seems very interesting in and of itself, just noticing that. Okay, so what we got here? 1 times our Planck boundaries, times the terminal action is 1, basically plus a sphere, times the first and second answers added together of the hyperbolic vortex equation, multiplied by our terminal boundary. Okay. What does that come out to be? It comes out to be this monstrosity right here. Okay. This monstrosity, as we can see. Okay. Planck length squared. That's times the Planck mass. That's over the Planck time squared. That's times the Planck temperature. And then we have our terminal action here. It comes out to be this. Okay. Let's go back to our number from the thing. Okay. So the number we are looking for here is 1.38. 1.38 064, 064, and 9. Okay, so 6, 4, and 9 are the last three. 6, 4, 8. Memes, you lied to us. You are a liar. You are incorrect. You are correct that I am incorrect, my friends. Welcome, Mark. It's okay. It's okay. You know what? Do I really understand what's going on here? Not really. I'm just trying to give my best approximation and be less wrong is all. That's what we're going for. We're all perfectly imperfect creatures. I've also spent about the past 2 years of my life investigating this and literally spent a week at a monastery as a physics monk sitting down and doing calculations and stuff like that. And I'm just barely starting to grasp what's going on. Basically, what do we have here? All right. This whole equation is we're trying to figure out a constant of nature. We have a particular prescription that when we follow it, we seem to be able to actually decode the constants of nature. Hey, welcome, Brandon. Thank you for joining, my friend. But, all right, these are essentially our ingredients. These are the Planck units. Now, when you type in the Boltzmann constant, Wolfram alpha, it actually tells you what they are. It's a method of cheating. It's like Game Genie for quote-unquote hacking the universe. So basically, what are these flavors? Mass, length, time, and temperature. Those are what we used in. Those minus signs mean you would put them, you would raise them to that power, but they would be in the denominator. That's literally what we did. See? Those guys are in the denominator, the ones with the negative numbers there. So here are our ingredients. We arrange the ingredients in a particular way, and then it's kind of like if you're cooking the ingredients, making a stew or soup, you gotta do some extra things to it. Maybe you stir it a little bit there. Coincidentally, stirring is kind of a circular motion. Maybe you're kind of treating it like pizza dough, and maybe it's kind of a sphere or something like that. Is this a perfect analogy? No, not at all. But basically, you got stuff doing things. That's really what it is. It's combinatorics. And we have Wolfram alpha to help us actually figure out the answers. So, again, now this last digit, because if we go over here, last digit, 2 digits is supposed to be 4 and 9. Okay. Why am I off? We have 4 and 8. But if we look a wee bit closer, what are the next 2 digits? 9, 9. Now, in some of these constants, they'll have error bars of like parentheses 13 or 60 or something like that, showing it could swing up or down either way. Now, in the scientific redefinition of the scientific units, one of the things that they mention is they use all this data and stuff and things to be like, what do we have a high level of approximation of it actually being? So they went to 1, 2, 3, 4, 5, 6. Oh, look, seven digits. That's interesting. 7 digits, and right there, like, all right, we have high confidence. It's a 9. What's that saying? Essentially, to the best of our measurements and calculations and stuff and things, it's going to be all zeros for the rest of it. Why do I say this? Number one, Thad told me it. And number two, when you plug in the Boltzmann constant, just type that word. It's like casting a spell. I summon the Boltzmann constant. It gives you this number here. 1.38064900. And you keep just doing more digits over here, more digits, fewer digits. 0, 0, 0. So we're assuming to the best of our measurements, and a lot of smart people around the world, we're assuming it's essentially zeros for the rest of it. So based upon this geometric derivation, I don't know, at least back in elementary school we were told if you got like a 5 or up, you round up. The next 2 digits are 9s, and then that's still above a 5 there. So my friends, I'm going to claim this is a geometric derivation to the Boltzmann constant. That's as many significant digits as you want. Why? Because it's geometry. And because we can. But that's all I got for right now. But hey, thank you all for watching. Peace out, everybody. Be safe. Take care of yourselves. It's a wacky world out there, but I got hope. I'm pretty sure the light is right around the corner. Take care of yourselves, everyone.
Have you guys checked out the Memes of Destruction's channel? He's an interesting dude. I like him.